Good afternoon, everybody. How are you today? Okay, it's a very nice, lovely day today. It's getting into a summer in Thailand at the moment. Today is the 18th of March, okay, 2021. And today we are going to do a topic on power factor correction. Okay, as you may remember, right? Power factor, or we write it as PF for short. The formula is cos of theta V minus theta I, right? And also PF, right? The PF value is sort of like it measures the efficiency of a power distribution system. Right, so anyway, I'm going to review some of the formulas that we have done for the past two sessions, okay, on the power that you may need to realize, okay, for this topic, the power factor corrections. So first of all, okay, we have done the triangle, right? Power triangle, okay, right angle triangle, right, with a angle theta V minus theta I right there, okay, and you should remember that the hypotenuse is the apparent power S, right, equal to VRMS IRMS. So therefore, if you use your trigonometry knowledge from middle school, you will find out that on this opposite of the angle side is the VRMS IRMS sine theta V minus theta I, okay, which is of course nothing but the formula for your Q, or your reactive power. And the unit of course is var, volt amp reactive. The unit of the apparent power is var, okay, and then on this side here, okay, adjacent side is of course VRMS IRMS cos theta V minus theta I, or this is your average power or real power or true power. All three names are used. Okay, so this is average power, and of course the unit is watt, okay, the unit is in watt, okay. And also the other day I was asking my students some questions about this formula, and it seems like that they were confused about the formulas. I'm gonna sort of like clear this a little bit in case you also have the same problem with my students here. So for example, the formula for complex power, okay, is phasor S. I put a vector on top indicating its phasor, and the formula is it's VRMS in phasor form and IRMS in phasor form conjugate, okay. So therefore, when it's in phasor form, it means that it has the magnitude, which is IRMS, and when I write RMS value as like an amplitude or magnitude of the phasor, I don't put any bar on top of it, okay, just a simple VRMS like this, okay. And so therefore this become VRMS phasor consists of VRMS, the magnitude, and the angle, the phase angle, right, multiplied by IRMS, okay, and the angle theta I, okay, theta I conjugate like this, okay. So in other words, it becomes VRMS IRMS, right, and the angle is theta V. Theta I conjugate become minus theta I. So this is your complex power. Okay, and the unit of course is var. Okay, so therefore these two terms is in a magnitude form. It's not in a phase. These two right here, it's a magnitude of VRMS and IRMS multiplied together, and this is your apparent power. So your apparent power S, right? Apparent power, okay, is the so-called the magnitude of your complex power, like this, right? So therefore, it's simply a multiplication of VRMS, the amplitude of VRMS, and the amplitude of the IRMS, like this. See? So there's a difference between when I have a bar on top and no bar. See, like that. So please, you have to make it clear that you don't get confused. Okay, when I write it as a phasor and as an amplitude. Okay, and of course, I will go on reviewing this. So you have a complex power, right, which is turn out to be VRMS, IRMS, angle theta V minus theta I. And of course, from if you use Euler's identity, it will be written as VRMS, IRMS, cos theta V minus theta I, plus J VRMS, IRMS, sine theta V minus theta I. And that is your average power, and this is your reactive power. That's why we can also write the complex power as P plus JQ. Unit is var. Okay, and of course this is also unit is var for the apparent power. Right, so please get all this formula straight. Okay, when it's phasor, when it's in a phasor form, when it's in an amplitude form. Okay, so now I'm going to go back, right? So that's a review on the formulas for power, right? Now back to power factor corrections. Okay, well, for the power, why do we need power factor corrections? Okay, well, what happened is that I will show you that in the reason why we need the power factor correction. Let's say that, okay, so why PF is important. Okay, right, so let's say that I have a factory. I have a factory here. Okay, I have a factory. Okay, factory, and this factory consume 100 kW. So there's a load, and it consume 100 kW with some PF. Okay, some PF lacking. Okay, so let's say in the first case, the PF is equal to 0.85 lacking. And let's see, I want to find the current, okay, that need to be fed to this load. Okay, fed to this load. So therefore, well, the problem say that the load is in watt. So this is your average power. You know it by the unit, okay, of the power. So therefore, we know that the formula is P equal to VRMS IRMS cos theta V minus theta I. Oh, and by the way, and they use a V equal to 220 volt RMS line. Okay, the voltage feeding the factory. So let's see. We know that P is 100K. We know that VRMS is 220. We don't know IRMS. We want to know that. Okay, find current, RMS current. Okay, and of course, cos theta V minus theta I is your power factor. So in this case, it's 0.85. So therefore, you will end up with the current is equal to 10 to the fifth divided by 220 divided by 0.85, and the answer is 534.8 amps. Okay. Now, if let's say that now change it to this PF, right? Same load, 100k watt, and it change the PF is now 0.95, lacking, higher. The value of PF is higher. So let's find the current also. So same procedure. So P is equal to Vrms, Irms, cos theta V minus theta I. So therefore, Irms equal to 10 to the fifth divided by 220. PF now is 0.95. And the answer is, let's see, 478.5 amps. Okay. Well, you can see clearly, right, that the current is reduced, right? When you compare the two, it reduced by 56 amp, about 10.5%. Okay. If you consider that, okay, you're gonna have the, the wire, the system, to be able to handle this current, of course, this one from PF 0.5, it will be a bigger, you need a bigger size, right? Than the one PF 0.95. So I suppose for the company, maybe, for this particular load, I would rather have PF is equal to 0.95 lagging, right? 0.95. Okay. Well, how about if I'm the generator, right? I'm a generator, the power company generator that had to generate this power. So if I am a generator like in Thailand, maybe EGAT or something, okay, the generating power company, okay, and there's transmission lines, transmission line, and it will have to go to this again, this factory, 100k watt load, okay, with some PF, okay, and considering that, well, the transmission line maybe has, let's say, to be like simple, 0.1 ohms, right, for the transmission line, okay. Well, the company, okay, use, 100k watt. So EGAT definitely has to, provide 100k watt to the factory, right? And of course, they are paid from what's inside here, right? So if there's any loss along this transmission line, right, this or along this transmission line, the loss, right, EGAT has to absorb it, right? The power company has to absorb it, okay? So let's see if you have like, the power generated by the source for each case, each PF. So therefore, we're going to find, the power, okay, generated, okay, in each case, okay, so is, PG generated equal to 10 to the fifth, right, which is of course this 100k watt to the factory, and of course the loss. So the loss is I square R, so this is R, and Irms square, okay. So the first case when PF is equal to 0.85 lagging, okay, so therefore the power company has to generate 100 times 10 to the 3 plus 0.1 ohms times the current was from PF 0.85 was 534.8 square, and so therefore it has to generate 128.6 k watt, okay, for the same 100k watt factory. What about if a PF is equal to 0.95 lagging? Okay, so in this case, the power company generate what is required by the factory plus the loss, okay, and the current here was 478.5 square. So therefore, it has to generate 122.9 k watt. So again, right, it's reduced, okay, it's reduced. The power station produced like, for PF of 0.85, the lower PF, the power company, right, produces about 5.7 kW more, okay, just to supply this 100k watt factory. So if you're a power company, of course, you would rather have that the company has, the load of higher PF. So therefore, of course, the power company, is not going to absorb anything that's not good for them. So they set up the rules that, the power company would charge you, charge the factories if your PF is, below certain values, right? So they will charge a penalty. So therefore, the company has the job to correct the PF to a point where they do not get fined. So therefore, why we need a method to correct the power factor. So therefore, higher PF is preferred. Okay, right. So now the best way is to look at an example how to correct a power factor. So let's say that I have a factory, okay, and a factory is, charge a penalty if the plant power factor drops below 0.85. So therefore, this factory is fed with 600 volt. The frequency is 60 hertz. Okay, and in the factory there are three major loads: lighting system, okay, a furnace represented by the impedance, okay, there's a current 150 amps pass through it, and this is 2.4 ohms, and this is 3.2 ohms, and there is a motor, okay, that consume 80 kW and 0.8 PF lacking. So there are three loads. Of course, all the loads are connected in parallel. Okay, connected in parallel. Therefore, let's start. Okay, by the way, the lighting system, okay, consume 12 kW. So three loads in parallel. Okay, we know only like 0.8 PF lacking, for this motor right here. Okay, so first step to do this is, of course, you have to find the power factor for all three loads together. Okay, so over all three loads, what is the power factor? So first step is you have to find the total average power and the total reactive power. So we go one by one. The first load is, of course, the lighting system. Okay, well, the problems indicated that there's 12 kW, and from just the unit watt, you know that this value has to be the average power. So P equal to 12 kW. If the question that's given to you didn't give you anything else, any PF lacking or anything with the reactive power, you can assume that the reactive power in this case is equal to 0 var. Okay. Second one, the second load, the furnace. Okay. The value that's given is the current and the so-called reactive part and the resistive part of the load. So therefore, the formula is P2 is equal to I square R. so equal to 150 square times R, which is 2.4. So it's equal to 54 kW. The reactive part, it's I square X. So therefore, it's 150 square times 3.2 ohms. So equal to 72 kVAr. Okay, so that's the second load. The third load, the motor. Okay, motor. Well, it said 80 kW. So you know right away that, okay, that's the average power. So P3 is equal to 80 kW. Q, right, the reactive part, you know that it's 0.8 PF, right, PF. So for this motor, if you apply the power triangle, okay, you know that, okay, you have this adjacent leg is 80 kW, right? You need to find this one Q here, right? To be able to find this, you need to know this angle, right? So the angle, where do we know it? We know it from, of course, the formula for the power factor. Because you know that the formula for power factor is equal to cos theta V minus theta I, and it's equal to 0.8. So therefore, the angle theta V minus theta I is equal to inverse cosine of 0.8, and therefore the angle is equal to 36.9 degrees. Okay, so you know that this angle here of your power triangle here is 36.9 degrees. So therefore now you have your set, right? You want to find Q, right? You know the adjacent side and you want to find the opposite side, and you know the angle. So the relationship is nothing but tangent, right? Tangent of 36.9 is equal to opposite over adjacent. So therefore your Q3 is equal to 80 kW times, right, tangent of 36.9 degrees, and the answer is 60 kVAr. So you have all three loads complete. So therefore your total average power for these factories is P1 plus P2 plus P3. So therefore equal to 12K plus 54K plus 80K. So therefore equal to 146 kW. For the reactive power, so it's Q1 plus Q2 plus Q3. So therefore equal to 0 plus 72 kVAr plus the last one is 60. So 60K. So the answer is 132 kVAr. Okay, so that's what you have. So you want to find out the power factor. Well, I'm gonna use this, make sure I understand it correctly, right? Power triangle again. So now I have 146 kW right here. The opposite is 132 kVAr, right? I don't know the angle yet, right? But I know these two sides, right? So therefore I can find the angle, tangent again, right? Because I know the opposite and the adjacent sides. So therefore tangent of something that I don't know, right? This angle equal to 132K over 146K, and the answer is 42.1 degrees. So now that I have that angle, I can go back to my formula for power factor. So therefore power factor is cosine of the angle of the triangle, so 42.1. So therefore the answer is 0.74. So is it below, what was the question? 0.85, right? So it's below 0.85. Definitely you will get fined, right? So this is below 0.85 from the set point that we need. So now we have to correct it, right? We want our PF from this 0.74 and correct it to 0.85. So therefore, well, if you need to know that PF is 0.85, the first step is we need to know, well, what would be my angle, because that's a formula that I know. So cosine theta v minus theta I. Can I write like new ones? Okay, is equal to 0.85. So therefore, my angle, the new angle that I need for this 0.85 PF is 31.8 degrees. 7.8 degrees, right? So that means if I'm going to compare this, my old, so back to power triangle again. So please, so understand how your power, triangle, right? So this is theta v minus theta I, right? Okay, hold on. Oops, sorry. This is before, right? So before the the original one with PF is 0.74. This is 42.1 degrees, right? And this is 132 kVAR, right? And this was 146 kW. These was the three loads, okay? But now I want PF is 0.85 and the angle is only 31.8, so the angle is lower than 42.1. So okay, let's just estimate this, right? So therefore now I get this Q, the new one, okay? Let me write that this is like my QO1, QO, right? The old one is 132. This is Q new one. I need to lower my Q to get PF, to get the angle of 31.8, okay? So what is it that can be added to my Q and it lower the values? Capacitor, inductor. I hope you think of a capacitor because it's a capacitor. Because capacitor has this, it's minus j omega 1 over omega c, minus jq. So it when you add the capacitor in, it sort of like reduced the Q, the value of your reactive power. So this is your Q, your reactive, so-called power for your capacitor. Okay. So in a way, you have a load, right? These are three loads that you have. To collect your power factor, you add a capacitor in parallel to your load. So your problem now is you have to find the capacitance value C to be connected in parallel to your load to increase your PF. So if you look from here, from this point of view, right, it seems that you see that, well, Q, if you have QC plus Q new, right, is equal to QO, right? This is your QO. Oh, what's going on? Right, please go away. Oh no. Oh no. What happened? Where do I go now? Oh, here. Okay, sorry. Okay. So therefore, right? So this is your QO, my blue color. The whole thing, right? So Q of a capacitor plus Q of the new PF is equal to Q of the old PF. So therefore, right, QC is equal to QO minus Q new. Right? But we don't know Q new yet. So let's find Q for the new PF, right? For the new PF, we know that this is 31.8 degrees. Your average power stay the same because we cannot add anything that will not change your average power, right? So the average power stay the same, but only the Q changes, the reactive power. So therefore, using again, right, trigonometry knowledge, skills, right? You have to remember that, right? Sine theta, cos theta, and tangent. What are the formulas? So therefore, what's about Q nu? To find Q nu, well, tangent, right? So tangent of 31.8 is equal to Q nu over 146 k watt. So therefore, my Q nu is equal to 146 k multiplied by tangent of 31.8 degrees. So my Q nu equal to 90.5 k var. So there I've got my Q nu. So I can put it here into this formula to find QC. So therefore QC equal to, my Q old value is 132 k var minus the new values 90.5 k var. So therefore I will get my QC equal to 41.5 k var. 41.5 k var. Okay. From here, okay, the formula for QC is equal to V square over XC. Your XC is a reactance values. So therefore, can find my XC equal to V square over QC. So V was 100 square from the problem, okay, and QC is 41.5 K. So therefore you get 8.67 ohms. So your reactance for the capacitor is 8.67 ohms. You want to find a value for the capacitor, and of course you have to remember XC is equal to 1 over omega C. So therefore your C is equal to 1 over omega XC. Omega is equal to 2 pi F. So therefore this problem, your capacitance value is 1 over 2 pi times 60 hertz times 8.67 ohms, and the answer is 306 microfarad. So therefore, to correct the power factor, you insert a capacitor, in this case 106 microfarad, right? This is your original load, the lighting, right, the furnace, and the motor. So in a way, if you look only from this point of view here, your PF was 0.74. You calculate it out, right, lacking. But if you look, included the capacitor in, your PF here will be changed to 0.85. And this is how you do the power factor corrections. Okay. Well, most of the load is of course inductive load. Most of the loads are normally turn out to be inductive load in the factory. So you will insert a capacitor, in parallel to those loads. Okay, but sometimes, okay, sometimes if the load is operating, at a leading PF, right? So pretty much like a capacitive load. Okay, then you connected, an inductor. Then, an inductor, is connected across the road for PF corrections. Okay, and your QL is equal to VIMS square over XL, okay, right, or equal to VIMS square over XL is of course omega L, right? XL is omega L, right? So therefore your inductor would be VRMS square over omega QL. Okay, so this is if somehow your load turn out to be a leading PF when you found it, the total when you found the total P and total Q, it turned out to be like that. Okay, so this is the steps of how you do it. So please go back and sit and try to understand the concept of it. Okay, understand the power triangle. Okay, so you have to remember the formulas, and it will be easier to work on things. So that's it for today on